So, I'm starting this channel for myself. Apparently, teaching someone helps you, and so I'm recording it. Me teaching y'all. And like most of you seeing this video, I'm also a 12th grader, and I just wanted to do it for myself so that I can listen to it afterwards. बाद में मैं सुन सकती हूँ and again revise it in my own style and hope that maybe some of you will like my style. If you don't, then that's okay. There are a lot of videos of NCERT line variant, but sure. I guess I'll skip this part. Types of solutions. Solutions are homogeneous mixtures of two or more than two components. By homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in large quantity is known as solvent. Solvents determine the physical state in which solution exists. One or more components present in solution other than solvent are called solutes. So basically solution are homogeneous mixture मतलब जो mix हो सकता है which we know already homogeneous and heterogeneous. And the major component is called a solvent which we know already. Most of this basic stuff we know. uh, and जो हम डालते हैं those are solutes. And until we shall binary solution consisting of two components, binary solutions which have two components. Here, each component may be solid, liquid, or in gaseous state and are summarized in this table. Oh, well, this table is important for NCQs. Like, the whole examples thing, like gas, solid, solution of hydrogen and palladium, like, they can tell you that maybe ऐसा ऐसा solution है that liquid solution इनमें से which of these is liquid and liquid solution. I think it's easy, but it may come for a mark in boards. Expressing concentration of solutions. Okay, concentration terms we have seen in mole concept also, and here we are revising it again in a more in like we are revising it again, but a few more things are added. So let's see. Composition of solution can be described by expressing its concentration. The latter can be expressed either quantitatively or qualitatively. Well, for example, qualitatively, we can say that the solution is dilute, relatively very small quantity of solute, or it's concentrated, relatively very large quantity of solute. But in real life, these kinds of descriptions can add to a lot of confusion. Thus, the need of quantitative description of solution. So basically, we know that the whole थिंग कि डाइल्यूट है concentrated है but then again I think according to these people that is very complicated confusing not for me though like I think इससे ज़्यादा तो इससे ज़्यादा तो यही confusing है but sure if they say so. There are several ways by which we can describe the concentration of the solution quantitatively. Mass, percentage, weight by weight. Now, while you are watching this video, I suppose you are also taking notes. So I think in this whole concentration terms, you can just write like mass, percentage, weight upon weight, and then the formula. I think that's enough. Or maybe a example, but I don't think example is necessary. So mass percentage weight upon weight, which is basically mass of component in the solution upon total mass of solution into 100 for the percentage. For example, if a solution is described by 10% glucose in water by mass, it means that 10 gram of glucose is dissolved in 90 gram of water. Like सो जितना परसेंटेज है उतना तुम्हारा वेट है और बाकी का बचा हुआ इज द रिमेनिंग पार्ट रिजल्टिंग इन 100 ग्राम solution. Concentration described by mass percentage is commonly used in industrial and chemical applications. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. Maybe this can come from 1 mark, but the chances are very less. uh, Volume percentage, volume upon volume. The volume percentage is volume of component upon total volume of solution. That was mass and this is volume into 100 for the percentage. For example, 10% ethanol solution is in water means that 10 ml of ethanol is dissolved in water and the other one is 90 ml is the other one, and so the solution is 100 ml. And this is used in cars for cooling the engine, and antifreeze. Basically the antifreeze lowers the freezing point of water to 255.4 Kelvin, which is minus 17.6 degree Celsius. Mass of volume percentage. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. In mass, it is mass of solute dissolved in 100 ml of the solution. So इससे पहले हम लोग देख रहे थे कि it's almost like it's the mixture of the mass and the volume thing, that mass of the unit, medicine or whatever mass of the solute used, and the remaining in the 100 ml. Like if you use sugar, 10 gram sugar and 100 ml water, basically that kind. Parts per million. When a solute is present in trace quantities, it is convenient to express concentration in parts per million, and it is defined as number of parts of the component upon total number of parts of all components of solution into 10 to the power 6. Now this is the example. Uh, as in the case percentage, concentration in parts per million can also be expressed as mass to mass, volume to volume, mass to volume. A liter of seawater weighs 1030 grams, contains about 6 into 10 to the power minus 3 grams of dissolved oxygen. Such a small concentration can also be expressed in 5.8 gram per 10 to the power 6 gram, which is 5.8 ppm, which is parts per million of seawater. So like जो बहुत छोटी quantities होती है, like कुछ बहुत basically like nucleus, if you guys know, it's very small. So like अगर कोई चीज़ बहुत ही छोटी है किसी बहुत ज़्यादा solution में, so you can describe it in parts per million. Like it has to be a huge quantity जिसमें बहुत ही small quantity is there. The concentration of pollutants in water or atmosphere is often expressed in terms of mu gram, or yeah, this parts per million. Mole fraction. Now, mole fraction is a very important topic. Not important, but important in terms of um, one markers. In recently in JEE, a question came from mole fraction. Like, like this exact thing came. So I guess you just need to remember this, which is very easy to be honest. Like number of moles of component upon total number of moles of component, which gives you the mole fraction. Like अगर तुम्हें किसी ए का तुम्हें मोल फ्रैक्शन निकालना है तो मोल्स ऑफ ए अपॉन मोल्स ऑफ ए प्लस मोल्स ऑफ बी, एंड सेम गोज फॉर अगर तुम्हें ए का निकालना है तो सारे जितने ए बी सी डी जितने भी है उतने ऐड कर दो. Mole fraction unit is very useful in relating some physical properties of solution, say vapor pressure with concentration of the solution, and quite useful in describing the calculations involving gas mixtures. So you'll have to use this whole mole fraction thing later on while solving numericals. जब तुम्हें गैस मिक्सचर दिए होंगे वेपर प्रेशर एंड कॉन्सेंट्रेशन उस केस में, like they have used over here this example जिसमें first calculate the mole fraction. Of course the question which you will get in exam won't be this easy. This is just to show you how you calculate the mole fraction, but sure. So to calculate mole fraction of X glycol, They first calculate the moles of this, and then of course moles of this upon the total moles, and you get mole fraction of water can also 1 minus, yeah. Now, the next concentration terms is molarity. Molarity is something which we are very familiar with, of course, after mole fraction, and uh, which is basically molarity. Moles of solute upon volume of solution in liter. Now, this whole liter thing, keep in your mind. Don't forget moles of solute upon volume in solution in liter. If you are given in other unit, change it. Literally change it. Don't forget this. Volume of solution in liter. यहाँ पे एग्जांपल दिया है, you can go through it. Molality, भाई of molarity. So moles of solute upon mass of solvent at kg. That was in liter volume, and this is in mass of solvent in kg. So in kg, again guys, please keep units in mind, because I am dumb and I have done the same mistake of not changing units on anything, and I really, yeah, वो felt pathetic after doing that. इतनी छोटी सी चीज़ों से भी फ़र्क पड़ता है. So keep the units in mind. And index questions. So I think I'll make another video where I'll just solve these questions. But if you want to try, you can try it. Like, these are very easier ones. Like, ये तो easy है. Real question पीछे है. Solubility. Okay, solubility of substance is maximum amount that can be dissolved in specific amount of solvent at a specified temperature. It depends upon the nature of solute and solvent, as well as temperature and pressure. Let us consider the effect of these factors in solution of solid or a gas in a liquid. सो सॉलिबिलिटी बेसिकली इज़ दैट कितना तुम अमाउंट एक चीज़ में डिज़ोल्व कर सकते हो एक स्पेसिफिक अमाउंट में और एक स्पेसिफिक टेम्परेचर में. लाइक लाइक पानी में कितना तुम शुगर डिज़ोल्व कर सकते हो, उसकी सॉलिबिलिटी वैसे काइंड. ओके. एंड तो अब इस चैप्टर में मेन चैप्टर यहाँ से शुरू होता है, बेसिकली सॉल्यूशंस. तो अब हम देखेंगे यहाँ से द सॉलिबिलिटी इन डिफरेंट टाइप्स ऑफ लाइक मिक्सचर, लाइक सॉलिड इन अ लिक्विड जो पहले आता है, और गैस इन अ लिक्विड. सो आवर फर्स्ट टॉपिक इज solubility of solid in a liquid. Every solid does not dissolve in given liquid. While sodium chloride and sugar dissolve readily in water, naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvents and non-polar solutes in non-polar solvents. In general, a solute dissolves in solvent if the intermolecular interactions are similar in two, or we may say like dissolves like. So basically, they are saying that with the example, suppose sodium chloride and sugar है, वो पानी में easily मिक्स हो जाते हैं, बट नैप्थलीन और एंथ्रासिन नहीं होते. क्यों? क्योंकि जो सोडियम क्लोराइड दोनों है वो पोलार सॉल्यूट्स हैं, एंड दे डिजॉल्व इन पोलार सॉल्वेंट. एंड नॉन पोलार सॉल्यूट है जो नॉन पोलार सॉल्वेंट में मिक्स होते हैं. So basically, the only thing which you have to remember from here is like dissolves like, and the example that naphthalene and anthracene dissolve readily in benzene but not in water. When solid solute is added to solvent, some solute dissolves and its concentration increases in solution. This process is known as dissolution. Some solute particles in solution collide with the solid solute particles and get separated out of solution. This process is known as crystallization. A stage is reached where the two processes occur at the same rate. Under such conditions, number of solute particles going into the solution will be equal to the solute particles separating out of a state of dynamic equilibrium is reached. So basically, there are two processes over here. तो डिसोल्यूशन मतलब जब जितना तुम जो सोल्यूट है वो सॉल्वेंट में मिक्स करते जाओगे उतना वो सोल्यूट का कॉन्सेंट्रेशन बढ़ता ही जाएगा, लाइक अंडरस्टैंडेबल ऑफ कोर्स। अगर तुम पानी में चीनी मिला रहे हो तो चीनी का कॉन्सेंट्रेशन बढ़ जाता है अंटिल द पॉइंट वेयर चीनी कैन नॉट डिजॉल्व एनी मोर, एज वी हैव सीन आफ्टर सम पॉइंट। लाइक अगर तुम बहुत ज़्यादा चीनी मिक्स करोगे तो ऑफकोर्स जितना पानी है उससे ज़्यादा करोगे तो इट वोंट मिक्स एट आफ्टर सम पॉइंट, आफ्टर थोड़ा वो डिज़ोल्व होने के बाद तो वो मिक्स नहीं करेगा। एंड क्रिस्टलाइजेशन वी हैव सीन कि जब बहुत ज़्यादा हम कॉन्सनट्रेटेड सोल्यूशन बना देते हैं एंड वी लीव इट देयर एंड क्रिस्टल्स फॉर्म हो जाते हैं, वो वी हैव डन दिस एक्टिविटी बिफोर ऑफ क्रिस्टलाइजेशन, आई गेस इट वाज इन 11th grade टू। उसमें they like you make a very concentrated sugar or salt solution and then you hang a rope ऐसे पेंसिल से बांध के in a glass of that concentrated solution, leave it for a few days and जो छोटे छोटे क्रिस्टल है वो उसके ऊपर चिपक जाते हैं। and we have also seen those क्रिस्टल कैंडीज जो ऐसे स्टिक पे होती है, आई थिंक दे आर मेड द सेम वे। सो दैट इज़ देयर एंड ऐसा जब स्टेज आ जाता है जहाँ पे ये दोनों ऐसे जितना तुम सल्यूट पार्टिकल्स अंदर जा रहे हैं उतना ही सल्यूट पार्टिकल्स बाहर भी आ रहे हैं, लाइक ये दोनों सेम पॉइंट पे आ जाते हैं डिसोल्यूशन एंड क्रिस्टलाइजेशन, तब ये डायनामिक इक्विलिब्रियम रीच हो जाता है। तो दैट इज़ what is given in this paragraph, solute plus solvent gives solution and तब वो पूरा मिक्स हो जाता है। At this stage, the concentration of solute in solution will remain constant under the given condition. तो इसलिए after the certain point the equilibrium, उसके बाद वो शुगर डिजॉल्व होती ही नहीं है, तो इसके बाद वो पीक पॉइंट पे पहुंच जाता है टेम्परेचर एंड। तो इन एनी कंडीशंस जो अमाउंट कॉन्सेंट्रेशन ऑफ सोल्यूट इन सोल्यूशन है वो सेम ही रहता है, भले ही तुम कुछ भी कंडीशन चेंज कर दो, टेम्परेचर, प्रेशर। Similar processes is followed when gases are dissolved in liquid solvents. गैस में भी सेम ही होता है। Such a solution in which no more solute can be dissolved at the same temperature and pressure is called saturated solution. We know well. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is dynamic equilibrium with undissolved solute is saturated solution and contains the maximum amount of solute dissolved in given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. So, basically, they are saying that अनसैचुरेटेड सोल्यूशन जो होता है जिसमें तुम और मिक्स कर सकते हो उसी टेम्परेचर पे, एंड इन्होंने बोला है कि जो सोल्यूशन है जो उनका जब वो डायनामिक इक्विलिब्रियम पहुंच जाता है and undissolved solute in a saturated solution and contains maximum amount of solute dissolved in a given amount of solvent. सैचुरेटेड सोल्यूशन मतलब जो होता है जो इक्विलिब्रियम है उसके बाद वो और मिक्स नहीं करा सकता, बेसिकली द होल पॉइंट इज दैट ओके देयर इज नो नीड टू do so much brain work over here. They are just saying what is saturated unsaturated solution and जो concentration हो जाता है saturated solution बनने के बाद वही उस solute की solubility होती है। like जब शुगर, अगर तुमने थोड़ा सा पानी लिया है थोड़ा सा चीनी लिया, मैं सेम एग्जांपल ले रही हूँ क्योंकि इट्स ईजी। सो अगर तुमने थोड़ा सा पानी थोड़ा सा चीनी लिया है एंड यू मिक्स इट एंड आफ्टर सम पॉइंट चीनी डिजॉल्व नहीं हो रही, मतलब उस जो कॉन्सेंट्रेशन उस चीनी का उतने पानी में वो उस चीनी की सॉलिबिलिटी है कि तुम कितनी चीनी उस पानी में डिजॉल्व कर पा रहे हो उस टेम्परेचर पे। तो लेट्स सी इफेक्ट ऑफ टेम्परेचर ऑन सॉलिबिलिटी। तो basically, okay, let's read. The solubility of a solid in liquid is significantly affected by temperature changes. Consider the equilibrium present by equation. This being dynamic equilibrium must follow Le Chatelier's principle, जो हमने chemical equilibrium में देखा था in 11th grade. In general, if nearly saturated solution, the dissolution process is endothermic. So delta H of solution is greater than 0. The solubility should increase with the rise in temperature, and exothermics delta is less than 0. The solubility should decrease. These trends are also observed experimentally. So basically they are basically saying that जो solubility है वो temperature के साथ increase करती है, and solubility जो है वो temperature के साथ डिक्रीज भी करते हैं। मतलब अगर तुम्हारी टेम्परेचर बढ़ रहा है तो सॉलिबिलिटी भी इंक्रीज होगी, टेम्परेचर घट रहा है तो सॉलिबिलिटी भी डिक्रीज होगी। एंड जब टेम्परेचर बढ़ रहा होता है तब वो एंडोथर्मिक प्रोसेस होता है, एंड जब टेम्परेचर घट रहा होता है तब वो एक्सोथर्मिक प्रोसेस होता है। Effect of pressure. Pressure does not have any significant effect on solubility of solids and liquids. It is so because solids and liquids are highly incompressible and practically remain unaffected by change in pressure. So pressure का इतना कुछ difference नहीं होता. Though in I guess gas, not I guess, though in gas there will be. Continuing with solubility of gas in a liquid. So many gases dissolve in water. Oxygen dissolves only in small extent in water. It is dissolved oxygen which sustains aquatic life. On the other hand, hydrogen chloride gas HCl is highly soluble in water. Solubility of gases in liquids is greatly affected by pressure, temperature. The solubility of gases increase with increase in pressure. For solution of gases in solvent, consider a system as shown in Figure 1.1. This is the figure 1.1. The lower part of the solution and upper part in gaseous system at pressure P and temperature T. Assume the system to be in state of dynamic equilibrium. Under these conditions, rate of gaseous particles entering and leaving the solution phase is same as we have seen earlier. जो डायनामिक इक्विलिब्रियम होता है उसमें the number of particles going in and coming out is the same. This Now increase the pressure over the solution phase by compressing the gas to a smaller volume. This will increase the number of gaseous particles per unit volume over the solution, and also the rate at which the gaseous particles are striking the surface of solution to enter it. The solubility of gas will increase until a new equilibrium is reached, resulting in an increase in pressure of gas above the solution, and thus its solubility increases. So basically इस पूरे पैराग्राफ में बोला है यूजिंग दिस एग्जांपल कि प्रेशर अगर बढ़ रहा है तो गैस डिजॉल्व बढ़ रही है, सॉल्युबिलिटी बढ़ रही है, एंड गैस मोल्स बढ़ रहे हैं, क्वांटिटी बढ़ रही है. um, So basically, if you see over here, ये जो बीकर है इसमें of course the amount of gas moles जो per unit volume है वो कम है because इसमें ज़्यादा area है, and when you compress this something, the amount of the gas moles or the solute, if we like imagine, increases. Of course they increase and the new solubility will come, and because solubility मतलब the concentration है, of course अगर ज़्यादा एरिया होगा तो ज़्यादा कम concentration होगा, and इसमें of course you can see that the concentration of the particles becomes more per unit volume, so thus the solubility increases. Pretty common sense वाली बात है. तो Henry's law. So Henry's law is a very important thing. It can come in exam to state, to write the whole. There's a statement and its equation, to solve examples. It's basically very important, and you need to learn the whole statement very nicely. So let's see. Henry was the first to give a quantitative relation between pressure and solubility of gas in a solvent, which is known as Henry's law. The law states that at constant temperature, the solubility of gas in a liquid is directly proportional to the partial pressure of gas present above the surface of the liquid or solution. Process it. Process the whole thing. So ये बोल रहे हैं कि जो सॉलिबिलिटी होती है गैस के अंदर, गैस इन अ लिक्विड इज डायरेक्टली प्रोपोर्शनल, जो तुम्हारा पार्शियल प्रेशर ऑफ गैस है जो प्रेजेंट अबव द सरफेस है। जैसे इस एग्जांपल में भी देखा, जो सॉलिबिलिटी होगी वो डायरेक्टली प्रोपोर्शनल होगी जो तुम्हारा पार्शियल प्रेशर है अबव द गैस, प्रेजेंट अबव द सरफेस ऑफ द गैस, लिक्विड और सोल्यूशन जो भी ये लिक्विड होगा उसके अबव जो पार्शियल प्रेशर होगा उसके प्रोपोर्शनल तुम्हारी सॉलिबिलिटी होगी। Dalton, a contemporary of Henry, also concluded independently that the solubility of gas in a liquid solution is function of partial pressure of the gas. If you use the mole fraction of the gas in the solution as a pressure of its solubility, then it can be said that mole fraction of a gas in solution is proportional to the partial pressure of the gas over the solution. So yeah, uh, okay. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase is proportional to the mole fraction of gas in the solution, and it is expressed as P is equal to KHX. So using this equation, so this is the Henry's law, okay, and you need to. There's no other choice. You need to just read and like you need to learn this statement word by word if you want to get full marks. Of course writing in your own words will get you marks, but sometimes कुछ टीचर होता है जो दे आर लाइक एनसीईआरटी की ही लैंग्वेज चाहिए मुझे, तो यू बेटर लर्न फ्रॉम एनसीईआरटी की लैंग्वेज इन कोट्स. This is the, so like even if now if you get two marker basically is what जिसमें Henry's law पूछेंगे mostly. They will like state Henry's law, what does Henry's law say, ठीक है. And ये जो डाल्टन की थियरी है, they might ask this also. So you need to give the entire thing, like you need to tell this thing first, then the most common form, and then the equation, and tell what is kh, then what is x, and what is p. kh is Henry's constant, of course proportionality निकालने के लिए. If we draw a graph between partial pressure of gas versus mole fraction of gas in solution, then we should get a plot type as shown in figure 1.2. So इसमें हम देख सकते हैं mole fraction of HCl in solution है cyclohexane, partial pressure of HCl. तो इसमें जो मोल फ्रैक्शन है वो ए का बी से, सो लाइक इफ यू सी, क्योंकि लीनियर ग्राफ है, पी ए विल बी इक्वल टू के एच एक्स ए, पी बी विल बी इक्वल टू के एच एक्स पी, and likewise different gases have different kh values at the same temperature. This suggests that kh is a function of nature of gas, like I said. Now, it is obvious from equation 1.11 that higher the value of Kh at given pressure, the lower the solubility of gas in liquid. It can be seen in table 1.2 that Kh values for both N2 and O2 increase with increase of temperature, indicating that solubility of gases increase with a decrease of temperature. It is due to reason that aquatic species are more comfortable in cold water rather than warm water. Now, this thing can come for 2 marks too. Why aquatic species are comfortable in cold water rather than warm water? Now, let me clarify this one thing that I'm not good at this. I'm just reading line to line like a student would do, and I'm just hoping that it's like you're talking and मेरे साथ साथ आप भी रीड कर रहे हो, राइटिंग नोट्स. सो बेसिकली हेयर ये लोग बता रहे हैं कि टेम्परेचर के साथ अगर टेम्परेचर बढ़ रहा है सॉलिबिलिटी कम हो जाती है. दिस इज़ फॉर गैस इन अ लिक्विड. ओके, सो वी हैव एप्लीकेशंस ऑफ हेनरीज लॉ. इसका आया था हमें 4 मार्कर. बेसिक इसका आया था हमें 4 मार्कर एंड 3 मार्कर एंड 2 मार्कर. सो आई नो दिस इज़ अ वेरी इंपॉर्टेंट पार्ट. अगर इतनी बार एग्जाम में पूछा है तो ऑफ कोर्स इट इज़ इम्पॉर्टेंट. ऑफ कोर्स also this part, mostly the scuba divers thing. So let's just read. To increase the solubility of CO2 in soft drinks, the soda water, the bottle is sealed under high pressure. We all know this. We literally all know this कि जो solubility of CO2 in soft drinks इतने ज़्यादा प्रेशर में भरते हैं ताकि ज़्यादा से ज़्यादा फिज़ बन सके. जो तुम्हारी फिज़ होती है सॉफ्ट ड्रिंक्स में, इट इज़ CO2. वी नो दैट राइट. तो अगर तुम जितना जोर से उसके अंदर CO2 भरते हो उतना फिज़ क्रिएट होता है. दैट्स व्हाट द कोल्ड ड्रिंक मेकर्स यूज़. वी वुड हैव नेवर थॉट कि जो कोल्ड ड्रिंक्स होती है उसमें इतना केमिस्ट्री यूज़ होता है वो हम बाद में जाके पढ़ेंगे, लाइक व्हेन वी वर किड्स. बट हियर वी आर. Scuba divers must cope with high concentration of dissolved gases while breathing air at high pressure underwater. Increased pressure increases the solubility of atmospheric gases in blood. When divers come towards the surface, the pressure gradually decreases. This releases the dissolved gases and leads to formation of bubbles and nitrogen in blood. This blocks capillaries and creates medical condition known as bends, which are painful and dangerous to life. To avoid bends as well as toxic effect of high concentration of nitrogen in blood, the tanks used by scuba divers are filled with air diluted with helium, 11.7% of helium, 56.2% of nitrogen, and 32.1% of oxygen. तो बेसिकली जो स्कूबा डाइवर्स होता है, सो वी हैव सीन राइट, जैसे जैसे हम नीचे जाते हैं उतना प्रेशर जो है वो लाइक ग्रेजुअली कम होता जाता है, एंड जैसे हम ऊपर आते हैं तो प्रेशर लाइक मैं उल्टा बोल रही हूँ. जैसे जैसे कोई भी नीचे जाता है तो वो प्रेशर इंक्रीज होता है. जब वो लोग ऊपर आ रहे होते हैं तो वो अचानक से ऐसे जैसे हमें पता है व्हेन वी गो, जैसे ही हम एकदम एकदम गरम जैसे समर्स में खेल के हम अचानक एसी में आ जाते हैं तो वी फील अ लिटिल बिट सिक, और एकदम ठंडे से एकदम गरम चले जाते हैं. सेम काइंड ऑफ थिंग, नॉट सेम ऑफ कोर्स बट लाइक द आइडिया. सो जब वो ऊपर आ रहे होते हैं बेसिकली इतना प्रेशर वो अचानक से रिलीज हो जाता है तो वो बबल्स फॉर्म हो जाते हैं नाइट्रोजन के ब्लड में, एंड दे अपेरेंटली ब्लॉक the capillaries and are dangerous to life. To and इस condition को bends बोलते हैं, as well as toxic effects of. तो ये जो बैंड्स है इसको अवॉइड करने के लिए दे बेसिकली यूज दिस टैंक्स, जिसमें होता है 11.7% ऑफ हीलियम, 56.2% नाइट्रोजन एंड 32.1% ऑक्सीजन. सो दिस इज़ अ वेरी इंपॉर्टेंट एप्लीकेशन. सिर्फ स्कूबा डाइविंग पे भी हमें केस स्टडी आ चुकी है, लाइक दे वर लाइक why do they use helium in the tanks. So of course you will write why, which is to avoid this whole bends thing. And what is the principle behind scuba diving to Henry's law. ये सब पूछ सकते हैं पूछा है. At high at altitudes, the partial pressure of oxygen is less than that at the ground level. This leads to low concentration of oxygen in the blood and tissues of people living at high altitudes or climbers. Low blood oxygen causes climbers to become very weak and unable to think clearly. Symptoms of condition is known as anoxia. सो ये तो हमें पता है कि जैसे जैसे हम ऊपर जा रहे होते हैं जो प्रेशर है वो लाइक ऑक्सीजन का जो अमाउंट है वो कम हो जाएगा, एंड जो प्रेशर है वो यू नो इंक्रीजेस काइंड ऑफ. हमारे कान बंद होने लगते हैं एंड नाक नहीं बट कान तो बंद होते हैं. दिस लीड्स टू लो कॉन्सेंट्रेट. ऑक्सीजन का जो कॉन्सेंट्रेशन है वो कम हो जाता है बेसिकली. एंड दिस इज अ एप्लीकेशन ऑफ हेनरीज लॉ apparently. इफेक्ट्स ऑफ टेम्परेचर, तो जैसे हमने पहले सॉलिड्स में पढ़ा था टेम्परेचर के साथ साथ सॉलिबिलिटी बढ़ती है. तो अब हम गैस का पढ़ेंगे कि जैसे जैसे लेट्स जस्ट सी. Solubility of gases and liquids decrease with rise in temperature. इसमें सब उल्टा हो रहा है बेसिकली. तो solubility of जैसे जैसे टेम्परेचर इंक्रीज होता है solubility डिक्रीज होती है. When dissolved, the gas molecules are present in liquid phase, and process of dissolution can be considered similar to condensation, and heat is evolved in the process. We have learned this in last section that dissolution process involves dynamic equilibrium and thus must follow Lee Chatelier's principle. And dissolution is an exothermic process. The solubility should decrease with increase of temperature. समझ आ गया. सो अब तक जो हमने पढ़ा है वो बेसिकली था सॉलिबिलिटी ऑफ सॉलिड इन अ लिक्विड, जिसमें द मेन थिंग वाज फर्स्ट ऑफ ऑल कि जो पोलर सॉल्वेंट्स होते हैं पोलर के साथ मिक्स होते हैं, नॉन पोलर के साथ मिक्स होते हैं, सैचुरेटेड अनसैचुरेटेड, डायनेमिक इक्विलिब्रियम, and then we have seen what is solubility basically, and then effect of temperature for solid in liquid, जो solubility temperature के साथ increase होती है, and temperature अगर वो है तो वो एंडोथर्मिक है, एंड solubility जो है वो डिक्रीज होती है जब टेम्परेचर डिक्रीज होता है वो एक्सोथर्मिक है. एंड फॉर solubility of gas and लिक्विड प्रेशर के साथ solubility इंक्रीज होती है, गैस डिजॉल्व इंक्रीज होती है एंड स्टफ. एंड हेनरीज लॉ, application of Henry's law, also that solubility is inversely proportional to kH. This is a very important thing, लिख लो. देन टेम्परेचर के साथ solubility लाइक अगर टेम्परेचर राइज हो रहा है तो solubility कम हो जाती है. Then applications of Henry's law. First one is soda bottle. Second is scuba diving, bends ka condition. Third is altitudes. These three conditions are very important. So learn them. Then effect of temperature जो हमने पहले देख लिया है. That this is what we have learned up to. Then there are in text question again you can try them. Um, Next topic is vapor pressure of liquid solutions. Liquid solutions are formed when solvent is liquid. The solute can be a gas, a liquid, or a solid. Solutions of gases in liquid have already been discussed in section 1.3. पहले का section. In this section, we shall discuss the solutions of liquid and solid in a liquid. Such solutions may contain one or more volatile components. Volatile in the sense कि vapors. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solutions. Binary solutions जो हमने देखा है, which have two components. तो यहाँ पे हम देखेंगे liquid and solids in liquids. Um, so the first one we have is वेपर प्रेशर ऑफ लिक्विड सॉल्यूशंस. तो पहले एक बार देख लेते हैं कि इस टॉपिक में क्या क्या आ रहा है हमें. तो देर इज रॉल्स लॉ, वेरी इंपॉर्टेंट, डाल्टन्स लॉ ऑफ पार्शियल प्रेशर, and then there is Raoult's law. So the Raoult's law is the main thing over here. Then we have solids, liquids, non-ideal and ideal solutions, azeotropes, and इसके बाद what? So this is the solutions वाला part. इसके बाद आएगी colligative properties. Okay, let's. Okay, so vapor pressure of liquid solution. Let us consider a binary solution of two volatile liquids and denote the two components 1 and 2. So we have a solution of two volatile liquids, 1 and 2. When taken in a closed vessel, both components would evaporate and eventually an equilibrium would be established between vapor phase and liquid phase. Let the total vapor pressure at stage P total be P1 and P2। तो इस स्टेज पे जो टोटल प्रेशर है वो P1 प्लस P2 वो, like suppose there is this thing जिसमें there is x a एक्स ए नहीं, एक्स वन एंड टू ले लेते हैं। ओके, दिस इज़ वेरी हार्ड बट श्योर। एंड इसके इसका जो P1 होगा, ये वेपर प्रेशर्स है। P2, तो जो टोटल होगा P P1 plus P2, this is way too hard but sure. These partial pressure related to mole fraction x1 and x2 of those components 1 and 2 respectively. The French chemist, this is way too hard. Francois, Marte, Raoult, 1886 gave the quantitative relationship between them. The relationship is known as Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. So this thing कि जो partial pressure है, partial vapor pressure, it is proportional to the mole fraction, and when you remove the proportionality we get a constant, and that constant is P1 naught, which is vapor pressure of the pure component 1 at the same temperature. तो जो P2 होता है वो P2 naught x2, P1 है वो P1 naught x2, where P2 naught represents the vapor pressure of according to Dalton's law of partial pressures, the total pressure P total is P1 of P1 plus P2, and जब हम ये P1 और P2 which is P1 naught and x1, P2 naught and x2 add करते हैं, तो of course considering you guys are studying PC and math, इसमें आ जाएगा 1 माइनस x2 इंटू P1 नॉट प्लस x2 P2 नॉट, ये इसका मोल फ्रैक्शन x1 का मोल फ्रैक्शन हम 1 माइनस x2 भी लिख सकते हैं क्योंकि x1 प्लस x2, there's no point in writing, but I'll anyway write 1. Done. And which can be also written in P1 naught plus P P2 naught minus P1 naught into x2. यहाँ पे हमने ये बस अलग फॉर्मूला लिख दिया. You can use any TBH if you are, अगर आपको x1 DI नहीं है, निकालना ही नहीं है तो sure use this one. Following conclusions can be drawn from equation 1.16. This is 1.16. Total vapor pressure over the solution can be related to mole fraction of any one component. No shit. Total vapor pressure over the solution varies linearly with the mole fraction of component 2. Well, yeah. Depending on the vapor pressure of pure component 1, and total vapor pressure over the solution decreases or increases with the increase of mole fraction of component 1, क्योंकि dependent है. ओके, सो अभी हम लोग देखने वाले हैं यहाँ से the as you took the whole. Okay, first we'll see the graph. So a plot of P1 or P2 versus the mole fraction x1 and x2 for a solution gives a linear plot as shown. Yeah, yeah. Uh, in figure 1.3, these lines 1 and 2 pass through the points for which x1 and x2 are equal to unity. Yeah. Uh, P total. Similarly, the plot 3 of P total versus P total versus x2 is also linear. The minimum value of P total is P1 naught. ये है P1 naught, and maximum value is P2 naught. Um, and evidently P1 naught is less than P2 naught. The composition of vapor phase in equilibrium with the solution is determined by the partial pressures of the components if y1 and y2 are the mole fractions of the components 1 and 2 respectively in vapor phase. So यहाँ पे जो है ना तो एज एक एक्स्ट्रा इन्फॉर्मेशन मैं आपको दे देती हूँ. यहाँ पे जो ये वैल्यू होती है, दिस इज जस्ट एक्स्ट्रा इन्फॉर्मेशन. आई डोंट नो इफ यू गाइस वांट इट बिकॉज आई रिमेम्बर्ड इट. बट जो इसका अगर हमने ग्राफ बनाया, ये भी जो होता है वो ऐसा लीनियर ही आता है. एंड जो पी बी नॉट होता है उसका ऐसा हाइपरबोला में आ जाता है. अगर पी ए नॉट अगर पी बी नॉट से बड़ा होता है, अगर हम प्रेशर वर्सेस मोल फ्रैक्शन का ग्राफ बनाए एंड अगर ये प्रेशर वर्सेस मोल फ्रैक्शन इन वेपर फेस का, तो हाइपरबोला बन जाता है. And so we'll get there, but like just to clear this first. So P1 is equal to Y1. ये जो Y है, this is the vapor phase में mole fraction. In general, Pi is equal to Yi P total. तो बेसिकली हम ये भी लिख सकते हैं ना कि जो Y है, समझ Y1 इज इक्वल टू जो P1 है upon the whole pressure, something like this. लाइक ये दोनों 1 एंड 2 का मिला के, अगर मोल फ्रैक्शन अगर हमें वेपर फेज में चाहिए ही है, तो वी कैन राइट पार्शियल प्रेशर जो है x1 p1 नॉट अपॉन x1 p1 नॉट प्लस x2 p1 नॉट. While doing the sums, you will get there anyway, but this is the main idea behind it. Well, you guys tell me if you guys want notes. I can, of course, send the whole PDF of notes, but I don't think it really helps unless and until you write it yourself. So I would highly suggest that you write your notes yourself. So Rawls law as special case of Henry's law. So all this is a connected conspiracy. I'm just kidding. All this is connected. According to Rawls law, the vapor pressure of volatile component is given solution in a given solution is P1 is equal to x1 p uh, xi pi naught for pi. The solution of gas in liquid, one of the components is volatile and that exists as gas, and we have already seen that its solubility is given by Henry's law, which states that P is equal to KHX. If we compare the equations, Rawls law and Henry's law, it can be seen that the partial pressure of volatile components or gas is directly proportional to its mole fraction in solution. Only the proportionality constant Kh differs the P1 naught. Thus, Rolle's law becomes a special case of Henry's law, in which Kh becomes equal to P1 naught, which is the partial pressure, vapor pressure. तो बेसिकली दे आर ये दोनों को अगर हम कंपेयर करें यहीं पे है तो इसी का डिफरेंस आ जाता है, दोनों में मोल फ्रैक्शन है ही, इसी का डिफरेंस आ जाता है। वाओ व्हाट, या व्हाटएवर। तो इन दोनों ने इसको इक्वेट कर दिया एंड ये इक्वल टू ये जो वे पार्शियल वेपर प्रेशर है ये इक्वल टू इन्होंने हेनरीज कांस्टेंट कर दिया। तो the fundamental thing was this. So they made the Rawls law a special case of the fundamental, जो Henry's law, vapor pressure of solutions of solids and liquids. So अब तक हमने देखा liquids and liquids, जिसमें main part was Rawls law. Now we will see solids in liquids, जिसमें we have a very important topic which is we'll see. It's not really important, I think, but sure. Another important class of solutions consists of solids, dissolved, and liquids. For example, sodium chloride, glucose, urea, and cane sugar in water, and iodine and sulfur dissolved in carbon disulfide. Some of ये one marker. Physical properties of this solution are quite different from those of pure solvents. For example, vapor pressure, liquids at a given temperature vaporize, and under equilibrium condition, the pressure exerted by the vapors of the liquid over the liquid phase is called vapor pressure. We all know what vapor pressure is. In a pure liquid, the entire surface is occupied by molecules of liquid. If non-volatile solute is added to the solvent to a given solution, the vapor pressure of solution is solely from the solvent. ये जो पार्ट है, in a pure liquid, the entire surface is occupied by the molecules of the liquid. If non-volatile solute is added to the solvent to give a solution, ये तो there is a decrease in vapor pressure of the solvent. The vapor pressure of solution solely from the solvent alone. The vapor pressure of the solution at given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules. Thereby, the fraction of surface covered by solvent molecules get reduced. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. So, this is the आई कैन नॉट ड्रॉ अ स्ट्रेट लाइन फॉर रियल कौन तो जो इससे हमें बेसिकली ये बता रहा है। तो जैसे ही द नंबर ऑफ सॉल्वेंट मॉलिक्यूल्स एस्केपिंग फ्रॉम द सरफेस कम हो जाते हैं जब हम बनाते हैं सॉल्यूशन, तो जो वेपर प्रेशर है वो भी कम हो जाता है। The decrease in vapor pressure of solvent depends on quantity of non-volatile solute present in the solution. This, irrespective of its nature, तो पहले जो था वो नेचर ऑफ गैस पे भी डिपेंड कर रहा था, जो हमने पहले पढ़ा था, बट इसमें नहीं कर रहा क्योंकि ये सॉलिड एंड लिक्विड है, नॉट गैस एंड लिक्विड। वाओ, so smart. For example, decrease in vapor pressure of water by adding 1 mole of sucrose in 1 kg of water is nearly similar to produced by adding 1 mole of urea in the same quantity of water at same temperature. Great example, claps. Rawls' law in its general form can be stated as for any solution, the partial vapor pressure for each volatile component in the solution is directly proportional to its mole fraction. Yeah, I'm also processing it. So basically, ये भी वही बोल रहा है. For any solution, the partial vapor pressure for each volatile component in solution is directly proportional to the mole fraction. As if we didn't even know this. Same ही चीज़ है. For a volatile component, basically. In binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecules are present in vapor phase and contribute to vapor pressure. Let P1 be the vapor pressure of the solvent, X1 be the mole fraction, and P1 not be the vapor pressure in pure state. Then, according to Rolle's law, P1, wow, the proportionality constant is equal to the vapor pressure. वहाँ पे जो था वो partial vapor pressure यूज़ करते, यहाँ पे vapor pressure in solvent, and then there is vapor pressure in pure state. Then according to Rolle's law ऐसे वो linear graph बन जाता है. If a solution obeys Rolle's law for all concentration, its vapor pressure would vary linearly from zero to vapor pressure of the pure solvent. Zero to pure solvent. ऑलराइट. अगर ये रॉल्स लॉ फॉलो कर रहा है, अगर ऐसे उल्टा सीधा ग्राफ दे दिया बोलता है कि ये रॉल्स लॉ फॉलो कर रहा है, नहीं तो नहीं. Okay, we are on ideal and non-ideal solutions. Liquid solutions can be classified in non-ideal and ideal solutions on the basis of Rolle's law. तो अब यही जो बकवास, बकवास नहीं है, यही जो है लॉ, P1 Pi is equal to Xi into Pi नॉट, इसको यूज़ करके हम दो टाइप के सोल्यूशन बनाएंगे, जो है आइडियल सोल्यूशन एंड नॉन आइडियल सोल्यूशन. तो इसकी ना मैं समरी दे दूँगी. So basically, you guys start writing. I'm gonna essay. I'll tell. तो फर्स्ट ऑफ ऑल आइडियल सोल्यूशन ऐसे सोल्यूशन होता है विच फॉलो रोल्स लॉ फॉर ऑल रेंज ऑफ टेम्परेचर एंड कॉम्पोजिशन. सो बेसिकली अगर एक है डिवाइस नहीं, आई एम सॉरी मेरी हैंडराइटिंग थोड़ी इसमें, ओके लेट्स जस्ट अज्यूम. तो इसमें ए इंटरैक्शन है, इसमें बी भी इंटरैक्शंस है, ठीक है. आई कैन नॉट राइट, इसमें ए एन इसमें बी है, एंड इसका अलग से पी ए नॉट है, इसका अलग से पी बी नॉट है, ठीक है. अ, जब ये एक आइडियल सोल्यूशन बनता है तो इसमें जो ए इंटरैक्शन होता है, इसमें जो बी इंटरैक्शन होता है, जब ये रिजल्टेंट मिक्सचर बनाते हैं तब इसमें ए बी इंटरैक्शंस होती है, ए बी इंटरैक्शंस बन जाती है इसमें. तो अगर इसका वॉल्यूम 1 है, इसका वॉल्यूम 2 है, तो उन दोनों का मिला के इसका वॉल्यूम बन जाता है. दैट इज़ बेसिकली आइडियल सोल्यूशन. एंड इसका जो पार्ट जो वो जो भी पी पी ए नॉट जो पी टोटल हो जाता है वो पी ए नॉट प्लस पी बी नॉट हो जाता है. सो सारे से जैसे हम स्केलर क्वांटिटीज ऐड करते हैं वैसे. एंड इसमें देर आर ये few things to be noted down, so you guys better start writing. जो डेल्टा वी होता है ऑफ द वी मिक्स दैट इज़ ज़ीरो. डेल्टा एच मिक्स जो होता है वो ज़ीरो होता है, यहाँ पे जो लिखा है ये जो है वो द एंथैल्पी ऑफ मिक्सिंग है, एंड द वॉल्यूम ऑफ मिक्सिंग देन डेल्टा एस जो होता है, वेल यू नो, होल्ड अप अ सेकेंड. आई होप आपने बुक्स निकाल के रखी है. There's not much to write, of course, but like there are few things uh, to be noted. Okay, anyway, uh, sorry for the disturbance. A call came. So where were we? Enthalpy of mixing is zero, volume is zero, delta S of mixing entropy is positive. This is not given in the textbook, but I think you should know it. Delta entropy of one solute is 0, and delta G of the mixture is negative. Delta puri entropy is positive. Pa minus Pa naught, Pa is equal to Pa naught into X, same Rolle's law. So I think this is what it is. Um, Also, there's this point to be noted: कि no solution is ideal, like 100% ideal, but the solution which we consider are close to ideal. So keep that in mind. And so यहाँ पे example दिया हुआ है: solution of n-hexane, n-heptane, bromoethane and chloroethane, benzene, toluene, etc. ये जो है ये याद रख लो, एग्जाम्पल तो पूछेंगे. They'll ask, ये भी एक important part है. Maybe they can ask कि difference between ideal and non ideal and example दे दो, या MCQ में आया था हमें इनमें से कौन सा ideal है. So you guys need to know, at least जो mention किया है वो तो याद होनी चाहिए. मैं कुछ चीज़ें बता रही हूँ because I have given all exams, unit test 1, midterms 2, pre-board 1 2. So उसके हिसाब से मैं बता रही हूँ जो सबसे ज़्यादा पूछा है अब तक. Not that I am very expert at whole predicting things, but sure. Next is, whoa. Okay, once a non-ideal solution, इसमें there is a very important thing which is positive deviation and negative deviation. We'll see what that is. When a solution does not obey Rolle's law over entire range of concentration, then it is called non-ideal solution. The vapor pressure for such solution is either higher or lower than predicted by Rolle's law. If it is higher, then the solution exhibits positive deviation, and if it's lower, it exhibits negative deviation from Rolle's law. The plots of vapor pressure of the function of mole fractions for such solution are shown in figure 1.6. The cause of these deviations lie in the nature of the interactions at molecular level. The case of positive deviation from Rolle's law, A-B interaction are weaker than those of A-A and or B-B. Thus, in this case, the intermolecular attractive forces between solutes and solvent molecules are weaker than that those between the solute and solvent molecules. This means that in such solutions, molecules A or B will be easier to escape than pure state. This will increase the vapor pressure and result in positive deviation. Mixtures of ethanol and acetone behave in this manner. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between the host molecules and break some hydrogen bonds between them. Due to weakening of interaction, the solution shows positive deviation from Rolle's law. In solution formed by adding carbon disulfide to acetone, the dipolar, so carbon dioxide to acetone, the dipolar interactions between solute and solvent molecules are weaker than that. The respective interaction among the solute and solvent molecules. These solutions are also known as positive deviation. So the main thing is that positive deviation तब होता है जब जो हमारे लाइक यहाँ पे दिया है ए बी interactions जो होता है those are weaker than that of A and B. तो जब ना because they are weaker in such solutions, this will increase जो escape करने का जो like where वो easier हो जाता है उनका, and thus they will, it's basically a very understandable language, not gonna lie. So just think that जब उनके वीक हो जाते हैं बॉन्ड्स, वेपर प्रेशर बढ़ जाता है, and they show positive deviation where it is higher pressure, and the graphs are given over here. For yeah, I did as one out. The vapor pressure for ये positive का, I should not write. Positive deviation ये है जिसमें as you can see ये यूनिटी मोल फ्रैक्शन वर्सेस वेपर प्रेशर का है, इसमें हायर मोल फ्रैक्शन है. So for positive deviation also I have some things you might like to know, right? So delta V is greater than or equal to 0, delta H mix is greater than equal to 0, delta S mix is positive, delta G mix is negative, delta S total is positive, PA is greater than PA naught XA naught XA, PB is greater than the whole, P is greater than PA naught plus PA naught minus PB naught. PA is basically greater, यहाँ पे भी हम देख ही रहे हैं. एंड इसी का जो है वोल्टा वो होता है for negative deviation, intramolecular attractive forces between AA and BB are weaker than that. And जो P जो बात का होता है वो ज़्यादा होता है. Similarly, a mixture of chloroform and acetone form solution with negative deviation from Lord's law. This is because chloroform molecule is able to form hydrogen bond with acetone molecules, decreases the escaping tendency, and vapor pressure decreases, resulting in negative deviation. Starting with azeotropes, some liquids on mixing form azeotropes, which are binary mixtures having the same composition in liquid and vapor phase and boil at the constant temperature. In such cases, it is not possible to separate the components by fractional distillation. There are two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. So first, for this concept, first we'll need to know what is boiling point and freezing point. I know most of us know it, but I will still revise it. So, boiling point, which is TB, it is minimum temperature at which vapor pressure of substance is equal to external pressure, and its graph is like hyperbola. At At normal boiling point, the pressure external is equal to 1 atmospheric pressure, which we know. Same concept is used in pressure cooking and volume distillation. Speaking of freezing point, the temperature at which vapor pressure of solution of solid and liquid phase of substance is found to be same is known as freezing point, and its graph is somewhat like this. For liquid, and this is for solid, and this is for liquid. And between here, somewhere on this point, the freezing point comes. Now, azeotrope is a mixture जिसमें we have the same composition in both liquid and vapor phase, and they boil at same constant temperature. And there are two types of azeotropes now: minimum boiling point azeotrope and maximum boiling azeotrope. Let's see what it means. The solution which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition. For example, ethanol water mixture obtained by fermentation of sugars on fractional distillation gives a solution containing approximately 95% by volume of ethanol. Once this composition, known as azeotrope composition, has been achieved, the liquid and vapor have the same composition and no further separation occurs. So जिन सॉल्यूशन का लार्ज पॉजिटिव डेविएशन होता है, they are called as minimum boiling azeotrope, and we have seen already what gives positive deviation. And इसमें example दिया है ethanol water mixture का, and I think you have to learn this example. Now, the solution with that show large negative deviation from Raoult's law. For maximum boiling azeotrope at a specific composition, nitric acid and water is an example of this class of azeotrope. This azeotrope has approximate composition 68% nitric acid and 32% water by mass. This boiling point, this with a boiling point of 393.5 Kelvin. So basically, this azeotrope part is important for, of course, 5 markers. They can ask, क्योंकि 5 markers में there is section like there are ABCD, like ABC parts, not whole question is 5 marker. So they can ask कि what is azeotrope, what is minimum boiling azeotrope, give one example. So it makes it 3 marks का question. Now we have colligative properties and determination of molar mass. Now, okay, we there is a reason why colligative properties were they came into picture, which is let's see, in section 1.4.3, that we learned that the vapor pressure of solution decreases when non-volatile solute is added to a volatile solvent. These are many properties of solution which are connected with this decrease of vapor pressure. So ये जो होता है, there are a lot of properties which contribute, and these properties are somewhat called, or we gave it the name as colligative properties. So the different types of colligative properties: relative lowering of vapor pressure of solvent, depression of freezing point of the solvent, elevation of boiling point of the solvent, and osmotic pressure of the solution. All these properties depend on number of solute particles, irrespective of their nature, related to total number of particles present in the solution. Such solutions are called as colligative properties. Colligative is from Latin, co means together, ligar means to bind. In this following section, we will discuss these properties one by one. Now, we can use these properties to find the different like constants, of course. In elevation of point, we'll find the uh, of course boiling point. There is a new constant there. For freezing, also there is a new constant. So using these properties, we can find molar masses. Okay, relative lowering of vapor pressure. We have learned in section 1.4.3 that vapor pressure of solvent in solution is less than that of pure solvent, of course. Raoult established that lowering of vapor pressure depends only on concentration of solute particles and it is independent of their identity. The equation 1.20, we'll have to see which I think they mean the Rawls equation. Low Given in section 1.4.3 establishes a relation between vapor pressure of the solution, mole fraction and vapor pressure of solvent. Okay, the same the Rawls equation P1 is equal to x1 P1 naught. The reduction in vapor pressure of solvent delta P1 is given as P1 naught 1 minus x1. They just replaced the x2 component in the and same for delta P1 x2 P1 naught. In solution containing several non-volatile solutes, the lowering of vapor pressure depends on sum of mole fractions of different solutes. Delta P1 upon P1 naught. This is the mole fraction, and this is where the relative this This is where the relative lowering comes. The expression of the left side of the equation, as mentioned earlier, is relative lowering of vapor pressure and it is equal to the mole fraction. We are using the same principle of equating the vapor pressure, which we were first equating with the molar fraction. Now we are equating it with the relative lowering of vapor pressure since x2 is equal to here, N1 and N2 are number of moles of solvent and solute respectively present in the solution. For dilute solution, N2 is much more smaller than N1. Now, for here, N1 and N2 are number of moles of solvent and solute respectively present in the solution. For dilute solution, N2 is much more smaller than N1 as we read earlier. And we can write the equation for this as follows for relative lowering. The same thing, relative lowering of vapor pressure is equal to N2 upon N1 जो moles है का ratio और हम इसे M1 M2 upon W1 W2 से भी कर सकते हैं. Here, W1 and W2 are the masses, and M1 M2 are the molar masses of the solvent and solute, respectively. From this equation, we have seen similar. Okay, wait. From this equation 1.28, knowing all other quantities, the molar mass of the solute M2 can be calculated. So this is what we are using colligative properties for, to calculate the molar mass. And using this, if you're given all of these, like of course you have to find. If you have to find, you can find. If you have given, and then you can easily find molar mass of the solute. Next colligative property, the vapor elevation of boiling point. The vapor pressure of liquid increases with increase of temperature. We have seen this earlier. If it boils at temperature at which its vapor pressure is equal to atmospheric pressure, like I told before, boiling point is when the vapor pressure is equal to the external pressure. For example, water boils at 373.15 Kelvin, 100 degrees Celsius, because at this temperature the vapor pressure of water is 1.013 bar 1 atmosphere. We have also learned in last section that vapor pressure of solvent decreases in the presence of non-volatile solute. Figure 1.7 depicts the variation of vapor pressure of pure solvent and solution as a function of temperature. For example, the vapor pressure of aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. In order to make this solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent. Thus, the boiling point of a solution is always higher than that of boiling point of the pure solvent in the solution prepared. Maybe this can cover two marks that why the boiling point of the solution is higher than boiling point of the pure solvent. इसको underline कर लो, I think. Similar to lowering of vapor pressure, the elevation of boiling point also depends on number of solute molecules rather than their nature, similar to solids. A solution of 1 mole of sucrose in 1000 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let T be, तो ये है boiling point, the boiling point of pure solvent, and Tb be the boiling point of the solution. Tb naught is of solvent and Tb is of solution. This increases the boiling point. So delta Tb, so elevation and boiling point. This is delta Tb is equal to Tb minus Tb naught, means boiling point of pure solvent. Boiling point of the solution minus boiling point of pure solvent. Experiments have shown that dilute solutions, the elevation of boiling point is directly proportional to molar concentration of the solute. This is molality, and thus delta Tb is equal to Kb. Of course, after removing the proportionality, this Kb is now called as boiling elevation constant or molar elevation constant. Now, I'm not going to pronounce this, but you can. Ebullioscopic constant. The unit of Kb is kg mole inverse. Values of Kb for some common solvents are given in table 1.3. If W2 gram of solute of molar mass, M2 is dissolved in W1 gram of solvent, then molality M of the solution is given by this expression. And using this expression, if we substitute this value of M, oh, then we can find out delta TB, and delta TB में we can easily find out the value of ये यहाँ से exchange कर, तो हमें यहाँ से भी मिल जाता है M2. So using second colligative property we can find out M2 also. So the basically we are using these colligative properties to find out molar mass of the solute, and we can use it in different forms. अगर जो जो हमें values दिए तो वो तुम्हें identify करना होगा question में. Here are the examples. Depression of freezing point. Now this is the same thing, not same thing of course, but like it's freezing point, and see the point पे आ जाता है delta F, which is the freezing depression, is directly proportional to this KFM, जिसमें KF नया constant है जो है freezing point depression constant और molar depression constant. वो molar concentration ये दूसरा था. This was molar elevation. This is molar depression. Can relate to this one. The unit of KF is kg. Same thing. Values of Kf for some common solvents. Okay, we have to see this 1.3 table. If W2, is maybe we can use same formula. Just इसमें TF दिया है. We can see, right? Same ही चीज़ है. Of course, it's not same conceptually, but like the formula is similar. This is for determining the molar mass of the solute. We know that the quantities W1, W2, and delta Tf along the molar freezing point depression constant. The values of Kf and Kb, which depend on the nature of solvent, can be ascertained from following relations. So this is what it is. Kf and Kb अगर हमें इसके लिए निकालना है तो हम इसका यूज़ कर सकते हैं. इसका यूज़ करना ही है. To find out M2 first, we have to find out Kf to, yeah, basically to put in the equation. Here the symbols R and M1 stand for gas constant and molar mass of the solvent. This R तो हम सबको पता है, M1 भी पता है, respectively, and Tf and Tb denote the freezing point at the boiling point of the of the pure solvent, respectively, in Kelvin. Further, delta H fusion and delta H vaporization represent the enthalpies of fusion and vaporization of solvent, respectively. These. So this is the table basically. I don't think this is very necessary क्योंकि जो values होती है वो क्वेश्चन में दी होती है. अगर if it's necessary, I don't think I've used this table anywhere. Now, the last colligative property, which is osmosis and osmotic pressure. Now, this is a very interesting one. We have been studying about it since a pretty good amount of time, I guess. We all know osmotic pressure. Oh my god, osmosis होता है. हमने like बहुत पहले भी देखा है वो किशमिश वाली एक्टिविटी जब पानी में चली जाती है किशमिश तो like it becomes very jelly like soft बड़ी हो जाती है. So there are many phenomena which we observe in nature at our home. For example, raw mangoes shrivel when pickled in brine achar. Wilted flowers revive when placed in fresh water. Blood cells collapse when suspended in saline water, etc. तो ये एग्जाम्पल हमें याद रखना है. If we look into these processes, we find one thing common in all, that is all substances are bound by membranes. These membranes can be of animal or vegetable origin, and these occur naturally, such as pig's bladder or parchment, or can be synthetic, such as cellophane. These membranes appear to be continuous sheets of films, yet they contain a network of submicroscopic holes or pores. Small solvent molecules like water can pass through these holes, and but the passage of bigger molecules like solute is hindered. Membranes having this kind of properties are known as semi-permeable membranes. Like as the name suggests, I don't think that there is much to like dig deep into what semi-permeable membranes are. Like semi-permeable मतलब पूरी तरह permeable नहीं है, but like जो छोटे छोटे चीज़ें like थोड़ा बहुत permeable हो जाता है. Assume that only solvent molecules can pass through these semi-permeable membranes. If membrane is placed between the solvent and solution, as shown in figure 1 point, this. So this is the semi-permeable membrane. The solvent molecules will follow through the membrane, form pure solvent in the solution. This process of flow of solvent is called osmosis. So, if you need full marks, you of course need to learn this line by line. The process of flow of solvent is called as osmosis. The flow will continue till the equilibrium is attained. वो जो हायर से लोअर जाता है लोअर से हायर तो the flow of solvent from its side to solution side across semi-permeable membrane can be stopped if extra pressure is applied on the solution. This pressure that just stops the flow of solvent is called as osmotic pressure of solution. तो ये जो फ्लो है इसे हम रोकने के लिए एक प्रेशर लगा सकते हैं एंड दैट प्रेशर इज कॉल्ड एज ऑस्मोटिक प्रेशर. The flow of solvent from dilute solution to concentrated solution across a semi-permeable membrane is due to osmosis. The important point to be kept in mind is that solvent molecules always flow from lower concentration to higher concentration, right? The osmotic pressure has been found to depend on concentration of solution. Of course, क्योंकि अगर हम वो pressure, of course, because अगर तुम pressure जो गैस है अगर वो कम कॉन्सेंट्रेटेड होगी तो हमें ज़्यादा प्रेशर लगाना पड़ेगा, अगर ज़्यादा होगी तो कम प्रेशर लगाना पड़ेगा, बिकॉज कॉन्सेंट्रेशन पे डिपेंड करता है प्रेशर. ऑलराइट, depends on number of and the osmotic pressure of solution in excess pressure that must be applied to solution to prevent osmosis to stop the passage of solvent molecules to semi-permeable membrane uh, into the solution. This is illustrated in Figure 1.10. Osmotic pressure is colligative property as it depends on number of solute molecules and not on their identity. So this is what colligative properties are. It has been found experimentally that osmotic pressure is proportional to the molarity C of the solution at given temperature. Molarity, comma C of the solution concentration. तो ये जो होता है ये है osmotic pressure which is proportional, which is equal to CRT. R is the gas constant, of course, because it was proportional. तो here C को replace करके they have written number of moles upon volume, understandable. Here V is volume of the solution and in liters, of course, containing N2 moles of solution. In W, if W2 grams of solute of molar mass M2 is present in solution, then N2 is equal to W2 upon M2. तो इसको भी इसमें put कर देंगे and we'll get this. I forgot what this is called. Osmotic pressure into volume is equal to W2 RT upon M2, और M2 इससे भी हमें मिल जाता है molar mass of the solute. We all know this quantity. If we have all these quantities, we can easily find out the molar mass. Measurement of osmotic pressure provides another method of determining molar masses of solute. This method is widely used to determine molar masses of proteins, polymers, and other macromolecules. The osmotic pressure method has advantage over other methods as pressure measurement is around the room. Temperature and molarity of the solution is instead of molality as compared to other correlative properties. Its magnitude is large even for little dilute solution. This technique of osmotic pressure for determination of molar mass of solute is particularly helpful for biomolecules as they are generally not stable at high temperatures and polymers they have poor stability. So this can come for few marks, few नहीं 2 marks की why osmotic pressure method has advantage over other methods. Two solutions having same osmotic pressure at a given temperature are called as isotonic solutions. This is important. Like come for 2 marks, what is isotonic, what is hypertonic. When such solutions are separated by semi-permeable membrane, no osmosis occurs between them. For example, the osmotic pressure associated with fluid inside blood cell is equivalent to 0.9% mass upon volume sodium chloride solution called normal saline solution, and it is safe to inject intravenously On the other hand, if we place cells in a solution containing more than 0.9% mass upon volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called as hypertonic. जिसमें ज़्यादा है mass upon volume जो if salt concentration is less than 0.9% mass upon volume, the solution is called as hypotonic. If in the case of water will flow into the cells if placed in solution and they would swell, तो जो hypertonic है इसमें shrink हो रहा है and जो hypertonic है उसमें swell हो रहा है, like kishmish. If we keep it in water it swells. This is an example of M2 जो formula है उसे use करके. The phenomena mentioned in beginning of the section can be explained on the basis of osmosis. A raw mango placed in concentrated salt solution loses water via osmosis and shrivel into pickle. Wilted flowers survive when placed in fresh water. A carrot that has become limp because of water loss into atmosphere can place into water making it firm once again. Water will remove its cells through osmosis. When placed in water containing less than 0.9% mass upon volume, salt blood cells swell due to flow of water in them by osmosis. People people taking a lot of salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis. This resulting in puffing or swelling is called edema. Water move. This can maybe come in 1 mark. We don't know, like because this is kind of bio, but like the bends edma, these two things you have to remember. Water movement forms soil into plant roots and subsequently into upper portion of plant is particularly due to osmosis. The preservation of meat by salting and fruits by adding sugar protects against bacterial actions through processes of osmosis. A bacterium on salted meat or candied fruit loses water, shrivels, and dies. So we have seen this earlier too. Like if you have to make a little bit, like अगर तुम सब्जी बना रहे हो तो you have to add water. So like if you have to make a vegetable सब्जी बनानी है तो हम लोग we add salt before so that the सब्जी releases the water and it cooks itself instead of adding extra water. This is where osmosis comes in place. So these are the application. Keep in mind, I guess you will maybe you'll need, like maybe in 3 marker they can ask the write 3 application of osmotic pressure, osmosis, reverse osmosis, and water purification. Now this is very something which we all know. RO. The direction of osmosis can be reversed if pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out of the solution through semi-permeable membrane. तो उल्टा हो रहा है osmosis का. This phenomena जिसमें पहले जो solution था वो semi-permeable से जा रहा था and अभी जो pure solvent है वही semi-permeable membrane से निकल रहा है. So this is called as reverse osmosis and it is of great practical utility. Of course, very great because it is used in almost every home inside like every part of the world. Like RO is everywhere. Reverse osmosis is used in desalinization of seawater. A schematic setup where the process is shown in figure 1.11. This thing. Uh, when pressure more when pressure more than osmotic pressure is applied, pure water is squeezed out of the seawater through membrane. A variety of polymer membranes are available for this purpose. जो फ्रेश वाटर है वो सी वाटर से निकल जाता है, जो सॉल्ट वाटर है वो लाइक ऑफ कोर्स सॉल्ट जो बच जाता है क्योंकि seawater is generally salt water. The pressure required for reverse osmosis is quite high because because it would be done on a large scale, and because a workable porous membrane is film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. These days, many countries use desalination plants to meet their potable water requirements. So, this is reverse osmosis, and this is one application of reverse osmosis, which is RO for desalination. It can quite an important topic. This is the next questions. Now, abnormal molar mass. We know that ionic compounds, when dissolved in water, dissociate into cations and anions. For example, if we dissolve 1 mole KCl in water, we expect 1 mole of K plus and Cl minus ions to release in the solution. If this happens, there would be 2 moles of particles in the solution. If we ignore interionic attractions, 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 2 into 0.52 Kelvin, which is equal to 1.04 Kelvin. Now, if we did not know about the degree of dissociation, we could be led to conclude that the mass of 2 mole particles is 74.5 grams and mass of 1 mole of KCl would be 37.25 grams. This brings into light the rule that when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. Molecules of ethanoic acid dimerize in benzene due to hydrogen bonding. This normally happens in solvents of low dielectric constant. In this case, the number of particles is reduced due to dimerization. Association of molecules is depicted as follows. It can be undoubtedly stated that if all molecules of ethanoic acid associate in benzene, then delta Tb, or like elevation of boiling point or depression in freezing point for ethanoic acid, will be half of the normal value. The molar mass calculated on basis of elevation in boiling point and depression in freezing point will therefore be twice the expected value. Such molar mass that is either lower or higher than expected or normal value is called as abnormal molar mass. So this is what molar mass is. Like, this is the main thing which you have to know. In 1880, Van 't Hoff factor was introduced, which is iota wala I, known as Van 't Hoff factor, to account an extent of dissociation or association. This factor I is defined as I normal mass upon abnormal molar mass, which can be written as observed colligative property upon calculated colligative property. This is more easier. Um, um, which can also be written as total number of moles of particles after association. ये dissociation वाला part तो खैर कट हो जाएगा. Total number of moles of particles after dissociation, number of moles of particles before association upon dissociation. Here, abnormal mass is experimentally determined molar mass, and calculated colligative properties are obtained by assuming the case that non-volatile solution is either associated nor dissociated. In case of association, value I is less than unity, while for dissociation it is greater than unity. For example, the value of I for aqueous solution KCl solution is close to 2, while other ethanoic acid and benzene is nearly 0.5. In conclusion, Van 't Hoff factor modifies the equation for colligative properties. Now, this is what the main thing which we have to remember is this and the Perroy formula. So first I'll tell you the like basic definition of Van 't Hoff factor. It is, if solute is an electrolyte, it's the number of particles. Its number of particles will change either due to dissociation or association, right? And thus, जो observed colligative property can be different from theoretical, theoretically expected property, and that is abnormal mass Van't factor. So we can add this Van't factor into all our colligative properties, which is ये सेम ही है, बस I मल्टीप्लाई हो जा रहा है हर जगह, I मल्टीप्लाई हो जा रहा है. Table 1.4 depicts values of the factor I for several strong electrolytes for KCl, NaCl, and GSO4. I values approach 2 as the solution becomes very dilute as expected. The value of I gets closer to 3 for K2SO4. like यहाँ पे closer to 3 हो जा रही है. Now the chapter has ended. This is the summary. Just read it. मेरे को तो पता है. And maybe in some video I'll do the exercise. Is my exercise is very long, and it is preferably like good अगर तुम यही exercise अच्छे से कर लो. And of course, sample papers, previous year questions are very important for this chapter, since this chapter is for I think 7 marks. So yeah. Also, I'd like to say that I'm not good at this teaching.